we know that MOSFET is a fully controlled active switch. It is also the fundamental of the electronic industry. Compared with the regular signal processing MOSFET, the power MOSFET should have higher voltage rating and current rating. And also its parasitic parameters are very important. So in this subsection, we will study the structure of and the operating principle of the power MOSFET. So first, let's plot the vertical structure of a typical power MOSFET. So the device is ground on the silicon die, right? So we can have multiple layers. So here is the N+ region, meaning heavily doped N-type silicon. Here is N- region, meaning lightly doped N silicon. And here we have a polysilicon layer. Or metal to wire out this N+ region. So this is the drain terminal of the N-type MOSFET. And within this N- region, we can grow a P-type region. P-type silicon. To formulate the body of the N-type MOSFET. And within this body, we can establish the source terminal, which is the N-type silicon. We can have multiple cells on the same silicon die. So this is the source. And between the drain and the source, we should have the channel, right? On top of the channel, we should have the gate terminal. Which is also constructed by polysilicon or metal. Usually we use polysilicon. And we know that MOS means metal oxide semiconductor. So we should have a oxide layer, right, which isolates the gate and the channel. So here we can have the silicon dioxide. To formulate this O layer. And so that will construct a basic fundamental MOSFET cell. But for power MOSFET, we should have very high current rating, which means that we should have lots of MOSFET cells in parallel, right? So we can establish lots of cells in the lateral direction. So here is another cell. Right, the gate terminal, and also we have the oxide layer surrounding it, and same here. And the oxide layer surrounding it. And besides this oxide layer, we should grow the polysilicon. The polysilicon is mainly in charge of wiring out the source terminal. So this can be treated as the source terminal. And also we can see that the polysilicon shorted the body and the source. So meaning that the source and the body have the same voltage potential. Okay, and also there's one more point I like to point out is here. So we can see that from the source to the drain, we have a PIN structure, which is indeed a power diode. So this is a parasitic body diode, which exists between the source and the drain terminal. And another one here. We have lots of them in parallel. Okay, so correspondingly, we can introduce the symbol of this MOSFET. Indeed, it's a four-terminal device: source, gate, body, and drain. Right. So we have two ways to represent the symbol. We can either use the four-terminal symbol, like gate, body, drain, source. We know that the body and the source are shorted, so we connected them together. And also we have a body diode. That is four-terminal implementation for the MOSFET symbol. Or we can use a simplified manner to use only three terminals because the body and the source are shorted by default. So this is the three-terminal representation for power MOS: the gate, source, and the drain, body diode. And in my class, I will insist on this type of symbol to represent the power MOSFET. Okay. Next, I will replicate this structure of power MOSFET to show you the principle for the on-state and off-state behavior for the power MOSFET. All right, we have copied these figures twice. So now let's try to analyze what happens in the off-state. So for the off-state, it means that we have no gate signal applied across the gate and the source. Consider that there is no voltage bias here. So then if we apply an external voltage source with positive on drain and negative on source, the device will be in off-state. So it should be able to bear such a high voltage rating. So now let's see what happens in this scenario. So if we apply a voltage, external voltage from the drain to the source, so here is the drain, right? Then we can see that this PIN diode will be reverse biased. Similar as what we analyzed before, the reverse biased will enhance the depletion region between the P and the N minus. So since this is N minus lightly doped region, we will have a wider depletion region width in the N minus region. So now let me construct this depletion region using the white chalk. So those shaded area in white color means that the mobile carriers are depleted. There are only ionized atoms left with the net charge, but this device cannot conduct current, right? the depleted region blocks the flow of the current, so which enable a high voltage rating of the power MOSFET in the off state, which is quite similar to the principle of the PIN dot. Okay. Next, let's look at what happens. Let me mark this depletion region. So next, let's look at what happens in the on state. On state means that we have a gate signal. Like this is gate, this is drain, this is source. Now we apply a gate signal to the MOSFET, meaning that we have a VGS with positive sign on the gate and negative sign on the source. Let's see what happens if we apply an external voltage source between the drain and the source. So first, the application for the gate and the source bias, meaning that there is a positive potential on the gate, right? So in the body has holes as majority carrier, but it also contains minority carriers, which are electrons. So positive voltage here will attract the accumulation of electrons in the channel. So the channel will construct a bridge between the source and the drain, so which formulate a pulse of electrons, right? Formulate a pulse like N to N channel to the N minus to the N plus pulse. So in this scenario, if we apply an external voltage source from the drain to the source, then the external voltage will push the electrons to flow from the source through the channel into the N minus region, into N plus region, into poly, into the drain. So the white arrow indicates the electron pulse. And accordingly, this will also have a flow of electrons. We know that electrons contains negative charge, so we will have the current flow, right? So let's mark the current pulse. The current pulse will be opposite to the electron flow. So meaning that we can have a current flow through from the drain to the source across this MOSFET channel. Okay, so that is the current pulse. We can see that the device is turned on. And also, there is one thing I like to emphasize is the value of the VGS. So basically, the VGS should be high enough, higher than the threshold voltage, to enable sufficient accumulation of the electrons in the channel to turn on the channel. Okay, this is a must for the MOSFET turn on. And also, we can see that in the current pulse, there is a bottleneck here, which is N minus region, right? So N minus region has the highest resistivity, right? So basically, we can say that the N minus region determines the on-state resistance of power MOSFET. Okay. And next, let's try to look at its IV behavior, IV relationship of power MOSFET. So we plot the x-axis as the VGS. Suppose here is like 15 volt, 10, 5. And this is the drain to source current, ID, like 10 amp. For a typical power MOSFET, we'll have such a profile for the ID versus VGS. Like, we have multiple curves. This one is for VGS equals to 0.5 volt. We can see that starting from this point to the right, meaning the device is on, right? This is mainly because the VGS is high enough. So higher than threshold voltage to allow the accumulation of electrons here to turn on the device. After the device is turned on, the current will rise with the increase of VGS, but slowly, right? But vertically, if we increase VDS, then the current will also increase. So we'll have such a profile. For example, this is VDS equals to 1 volt, even higher, like 2 volts, 5 volts, 10 volts. Like 200 volts, okay. With the increase of drain source voltage, if the device is turned on, the current will increase. And this region marks the off state, meaning that the VGS is not high enough. So the channel is not formed, so the current cannot pass. Okay, we have erased the blackboard. Now let's look at the parasitic capacitance of the power MOSFET. Parasitic capacitance. So first, let's plot the symbol of the power MOSFET. Physically, there will be 3 capacitance associated with this device, which exist like this is gate, source, drain. Between the gate and the source terminal. And also there is another one between the drain and the source terminal, and drain and the gate terminal. So this is marked as CGS. This is marked as CDS. This is marked as CGD. So the 3 capacitance have different behaviors. Like first for CGS, which is a gate to source capacitance. So usually this capacitance is large, and it's like constant. And for the CGD, this one is small, but it's also highly nonlinear. And for CDS, the value for CDS is in between CGD and CGS, so intermediate. It is also highly nonlinear. So the highly nonlinear meaning that the value for the capacitance will change with the voltage bias. For example, CDS, we have an imperial equation to describe it. So this CDS equals to a constant capacitance divided by square root 1 plus VDS over VO. So we can see that with the rise of the VDS, the CDS will decrease. That is what the word nonlinear means. And we can see those kind of capacitance profile in the datasheet for the power device. Usually in the datasheet, we have different notations to note those three capacitance. Like we have the CISS, like input parasitic capacitance. This input side equals to CGS plus CGD. And also we have COSS. So this will equal to CDS in parallel with CGD. And also we have the CRSS. It's like the bridge between gate and drain. So this will be equals CGD. And for example, if we can show you a typical example for a power MOSFET capacitor behavior. So VDS capacitance value, usually this will be in the dimension of picofarad. So suppose like 50 volt. 10, 20, 30, 40. And for the capacitance value, we usually have 2,000 picofarad, 1,000, 1,500, 500. If you look at a typical device capacitance behavior, for example, they will illustrate the CISS. And this is obtained in the test condition at frequency at 1 megahertz with the VGS bias at 0 volt. And also the COSS will be intermediate value. COSS equals CGD plus CDS plus CGD. Right? CDS is highly nonlinear, right? Meaning that changing rate is fast. And the CRSS also highly nonlinear. Okay. So that is the basic behavior. So here's volt. So what's the meaning for this parasitic capacitance? Actually, the switching speed is determined by the parasitic capacitance. So the switching speed determined by the rate gate drivers charge or discharge the CISS, which is CGS plus CGD. If we want to turn on the device, we have to charge this CISS to allow VGS to rise to sufficient high level, right? If we want to turn off, we need to discharge it. Okay, now let's try to summarize the MOSFET. So first, the MOSFET is a fully active controlled, right, active device. Meaning that it's quite different from diode. Both the turn on and the turn off are active controlled by the third terminal, which is a gate source bias voltage. And secondly, this device is a majority carrier device. This brings us significant benefits in the switching behavior because we no longer need to sweep the excess minority carrier devices when we turn off the device. So the switching speed can be fast. And fourthly, which is kind of a limitation for power MOS, so the voltage rating is limited. Usually for silicon MOSFET, we can only achieve like 200 to 300 voltage rating. If we want to achieve like 600 rating, we need to introduce the superjunction technology, or we can use a silicon carbon device. And next, fifth, the R-on, the turning on resistance will increase with the rated voltage. And sixth, it is easy to drive. For this one, if we have higher voltage rating, we need to have thicker N- region, right? So, but this N- region also serves as the bottleneck in the current parts, so our arm will also increase. And for this one, since it is a voltage control device, so we just use the very simple totem pole drivers to easily turn on or turn off the device. Till now, we have fully introduced the on-state and off-state of power MOSFET, and we can understand that it is a actively controlled and majority carrier device. It has the features of high switching frequency, but its voltage rating is also limited. The on resistance will increase with the voltage rating.